In this video, we're going to be looking at the application of finding the average value of a function over an interval. Some examples where you might be interested in finding the average value include situations like finding the average temperature of a city over the course of the day, finding the average velocity of an object, finding the average elevation of something like the average elevation of a mountain, or perhaps finding the average height of a wave. So these are all situations where you would have some kind of continuous function whose average you're interested in finding. So how can we find the average value of a function like that? Well, let's first just think about what we know about averages in general. We know if we have just n numbers, then to find the average of that list of n numbers, we'd add up all the numbers in our list and divide by how many we have. So we'd have something like y1 plus y2 plus dot 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 plus yn divided by n. So we have to think about how the situation is going to change when I have a function, y equals f of x, on an interval from a to b, whose average I'm interested in finding. Because here, if I think about adding all of the values of my function between a and b, that's infinitely many values that I have to deal with. So how can we think about averaging those different values? So what's the big idea? Well, the idea is to think about slicing and summing. So just like in many of our integral applications, we want to think about first breaking up this interval into lots of subintervals, and then looking at adding up something for each piece, for each of those subintervals. So we're going to divide our interval, AB, into n subintervals. Okay, and then we think about the ith subinterval here as being from xi minus 1 to xi, and we have some sort of sample point in that interval that we call our xi star. So at that particular point, I have the value f of xi star. Okay, so I can think about for each of my different intervals, I pick a point in the interval, and I look at the value of the function at that point. So in this way, we can get an approximation to the average. I can be adding f of x1 star plus f of x2 star, etc., all the way up to f of xn star, and dividing those by n. So for a really small interval, of course, this value here is approximately the value excuse me, of the function for the whole interval. So how can we turn this into something that we might recognize as a Riemann sum? Well, notice that when we did this division, we had the width of our interval was equal to b minus a over n. So n here, if I notice that delta x equals b minus a over n means n times delta x is b minus a, then n itself is b minus a over delta x. So that's how I can introduce delta x into this formula here. So I have f of x1 star, etc., all the way up to f of xn star, divided by now b minus a over delta x. Okay, so if I'm dividing by a fraction, I can multiply by the reciprocal. So I have 1 over b minus a times delta x times this sum of all my values. Okay, so we're getting really close to what our formula is going to be here for our average value. So notice that I can write this as 1 over b minus a times the sum from I equals 1 to n of f of xi star delta x. And so this is approximating my average value. But if I look at taking more and more subintervals, making n smaller and smaller, in other words, making n bigger and bigger, so the subintervals themselves are smaller and smaller, I'll be looking at the limit of that sum. So that brings us to our definition of the average value. Would have 1 over b minus a times the limit as n goes to infinity of that sum, I equals 1, all the way up to n of f of xi star delta x, and then we recognize that as one of our Riemann sums, as the definition of a definite integral. So this is 1 over b minus a times the integral from a to b of f of x dx. So that's what we'll be using as our average value formula. Excuse me. One intuitive way to think about this definition is that this integral from a to b of f of x is essentially adding up all of the values of the function between a and b, or integrals like a big sum, and then dividing by how big that interval is. So adding them all up and doing some kind of division piece. So let's just look at one basic example where we apply this average value formula. So I have this function, 4x minus x squared on the interval from 0 to 4. So applying our formula, let me scroll up so we can look at the formula at the same time. We have f average is going to equal 1 over b minus a, in this case 4 minus 0, times the integral from 0 to 4 of 4x minus x squared dx. So we go ahead and do our antiderivative. So we have 4x squared over 2 minus x cubed over 3. And this is going to be evaluated from 0 to 4. Okay, so we have 1/4. Let's see, this will be 2 times 4 squared minus 4 cubed over 3 minus 0 minus 0. Okay, so with a little bit of arithmetic here, let's see, this is going to be 32 minus 64 thirds. That'll end up being 1/4 times 32 thirds. So we'll have 8 thirds as the final answer for our average value. Okay, so let's just get one picture to go along with this. What does our function actually look like here? Well, this is an upside down parabola with intercepts here at 0 and 4, and the maximum occurring at 2. Okay, so we have a parabola looking something like this. Okay, and our average value here at 8 thirds, that's about 2 and 2/3. So around here, that's our average at 8 thirds. So we can see that that's sort of like the average height of our function over the interval. We can also see that it turns out that there's a point on our function that was actually equal to the average value. And that's a theoretical fact that we're going to see explained a little bit more in one of our later videos.